We learned yesterday that there's three things in the atom: protons, neutrons, electrons. It's really electrons that we're concerned about in this unit. They're the ones with negative charge, and they're the ones that move around if anything's going to move around. We talked yesterday as well about objects with charge, not individual charges like protons and electrons, but objects that are charged positive or negative. If we have an object that's charged positive, where does it come from? Like, what is it made up of? It's got protons, it's got electrons. So if it's positively charged, it means it has more protons. Yeah, it's got more protons than electrons. Now, if it's negatively charged, it means it has more electrons than protons, right? If it's positive, it means it's lost electrons. If it's negative, it means it's gained electrons. Now, we're going to learn later on today how that happens, how an object can either gain or lose electrons. But for now, we just know that it either has gained or lost electrons. Finally, if it's neutral, then it's going to have no charge. It doesn't mean it doesn't have protons and electrons. It just means it has an equal number of protons and electrons. Does that make sense? We talked yesterday about the unit of charge as well. It's the coulomb. Do you guys remember the symbol for charge? If the unit is the coulomb, the symbol was... Somebody said it, yeah, it's a lowercase q. We sometimes see it written in some books as a capital Q, but we're focused on, we're going to be consistent with our data sheet in Physics 30, which calls it a lowercase q. So for us, it's always going to be a lowercase q. Now, the coulomb is a really, really big unit of charge. It's a really big unit of charge. We said that a coulomb is so big that the charge of an electron is only 1.6 or negative 1.6 times 10 to the negative 19 of them. In other words, it takes 10 to the 19 electrons to make up a full coulomb of charge. Similarly, for a proton, it's positive 1.6 times 10 to the minus 19 coulombs. It takes 10 to the 19 protons to make up a coulomb of charge as well. Now, some of you may even remember these numbers from yesterday. Probably not. Probably not. By the end of the unit, you probably will. But if you don't, you can always find them on your data sheet. Where on our data sheet can we find the charge of an electron or a proton? You got to look in a couple places, right? Top right-hand corner, we see here that there's an electron that has a charge of minus 1e. What does that mean? Minus 1e. In chemistry, sometimes you learn that an electron has a charge of minus 1, right? Well, it's minus 1e. You just don't call it e in chemistry. You just say minus 1. What's an e? It's the elementary charge, good. 1.6 times 10 to the minus 19 coulombs. So an electron is negative 1.6 times 10 to the minus 19 coulombs. A proton is positive 1 times 1.6. What would an alpha particle be? Whatever an alpha particle is, that comes later on in the course. Charge of an alpha particle would be 3.2 times 10 to the minus 19 coulombs. And the masses are given to you there as well. Notice the mass of the electron, though. Take a look at the electron, 10 to the minus 31, 10 to the minus 27. Mass of an electron is like 1,000th the mass of the proton. So even though it has the same charge, it has a dramatically smaller mass. The electron is a fundamental particle, and protons are made up of other things, part of the reason why. Okay, we talked about isotope, or not isotope, but ion notation. Ion notation. As well, we have Al3+, that's aluminum 3+. What's the charge of an aluminum ion? Well, 3+, right? But 3 plus what? 3 times the elementary charge. Or this would be 4.8, positive 4.8 times 10 to the minus 19 coulombs. This would be 1 times the elementary charge, or 1.6 times 10 to the minus 19 coulombs. And this would be negative 2 times the elementary charge, or negative 3.2 times 10 to the negative 19 coulombs. Aluminum 3+, has it gained or lost electrons to become positive 4.8 times 10 to the minus 19? It's lost electrons, right? You don't become positive by gaining negative, right? You become positive by losing negative. Na+, same thing, and O2- became negative by gaining electrons. We looked at an example yesterday involving calculating the number of electrons. We're going to see not necessarily this question carry through the course, but a few times we're going to be asked to solve for a number of something, an amount of something. When you're looking for an amount of oranges, You divide the total mass of the bag of oranges by the mass of one orange. If you're looking for the total number of photons, whatever that is, that comes later in the course as well, you can divide the total energy by the energy of one photon. If you want to find the number of electrons, you're going to divide something total by something one. What is it? Whatever's convenient, right? We got charge here. We get the total charge, and we know the charge of one electron. So let's say negative 9.6 times 10 to the minus 9 coulombs divided by negative 1.6 times 10 to the minus 19 coulombs. Whatever we get there, I'm not sure what it is, but whatever we get is our number of electrons. Now, how do we know whether it's gained or lost? Is it electrons, however many electrons that is it that many electrons gained, or is that many electrons lost? Well, the charge of this balloon is negative 9.6. If it became negative, it must have gained electrons. You become negative by gaining electrons. You become positive by losing electrons. Now, we also talked about a conductor and an insulator yesterday. We differentiated between the two. Although there's a little bit of a misconception with these. It's not like two completely separate categories. It's more of a continuum. Everything will conduct electrons to some degree. Everything will allow electrons in the outermost regions to move around to some degree. Conductors just allow it a lot easier, that's all. What's a good example of a conductor? Yep. Copper is one of the best examples of a conductor. Another one? Aluminum is a good conductor, right? Gold is a fantastic conductor, better than copper or aluminum. Why don't we use gold as wiring in our houses? Well, because it's kind of expensive. Copper is expensive. Gold is just a little bit more than copper. But we do use gold. Have you ever noticed this? Sometimes when you buy a cable, like an audio cable or a video cable, it'll be gold-plated. The connection will be gold-plated. The reason being is because it's a better conductor. Gold's a really good conductor, and you don't get that interference. Yeah?
The original clarinet one had 24 karat gold plating in the engine bay to get rid of the heat better.
Is that right? Okay, interesting. I guess if you're spending several $100,000 on a car, maybe you can splurge on something like that, right? Yeah. An insulator, listen, insulators can conduct electricity. Air is an insulator. It's a pretty good insulator, in fact. But yet air sometimes conducts electricity from the cloud to the ground when we get lightning, right? Insulators will conduct, but not nearly as well as conductors will conduct. So we say for an insulator, generally the electrons aren't as free to move about, therefore they don't conduct as well as conductors. All right, finally, this is where we ended off yesterday, the 3 laws of electric charge. I should cover that up and see what you remember. You guys will get all 3 of these, right? Doesn't matter what order you give them to me in either, by the way. Tell me one of the laws, one of the 3 laws of electric charge that you learned in grade 9 and then again yesterday. Yep. Yeah, opposite charges attract. So positive attracts negative. Positive pulls negative towards itself, and negative pulls positive towards itself. We had a question on your momentum unit test about the impulse involved in a collision, right? The impulse was equal and opposite. Well, forces are always equal and opposite as well by Newton's 3rd law, right? So if you've got a positive and a negative, the positive pulls the negative towards it. It attracts it with a certain force. Well, the negative pulls the positive towards it with an equal and opposite force. Even if the charges are different, the forces would still be equal and opposite. The attractive force would still be equal and opposite. Final, the next one is, if we talk about opposite charges attracting, we would say like charges, or positive and positive, or negative and negative would repel each other, right? Too much alike, can't get along. Just like people sometimes, right? Like charges are going to push each other apart with equal and opposite forces. And finally, the 3rd one, which we're going to build upon here in a little bit today, the 3rd one says charged objects will attract, yes, neutral objects. Charged objects don't attract neutral. Charged objects attract neutral objects. That's important. The charged objects don't attract neutrons. Protons don't attract neutrons. Not electrically. There is that strong nuclear force that we talked a little bit about yesterday, Protons do attract neutrons by this nuclear force, but they don't attract them electrically. But rather, protons would attract neutral objects electrically. And again, you'll see why in a little bit. Okay, that's yesterday. Today I want to give you one more law. It's called the law of conservation of charge. Doesn't really fit with the other three, so that's why we separate it. It's like the law of conservation of anything else, really. The law of conservation of energy says energy can't be created or destroyed. The law of conservation of matter says matter can't be created or destroyed. The law of conservation of momentum, well, we phrased it as total initial momentum equals total final momentum. But really what it means is momentum can't be created or destroyed. Well, we say the law of conservation of charge says charge can't be created or destroyed. You can transfer it from one thing to another. The balloon was neutral. Now the balloon is negative after it's been rubbed against my hair. It's charged and it wasn't before, but the total amount of charge in the system had to remain the same because you can't create and you can't destroy it. So if you have a total charge of 0, it'll remain 0. Just rearrange it a little bit. If you have a total charge of -5, it'll remain -5. Just rearrange it a little bit. Back in our last unit, we looked at the back wall and saw and used two physics principles. Principle 0, uniform motion. Principle 1, accelerated motion. Now we've got another one. It's principle number 7, conservation of charge. Now the description that's below that isn't going to make any sense to you right now. 0 sense to you. But if you get a question like we're about to see, know that we were using principle number 7, conservation of charge. Right? Here's the question. We've got two charged objects of similar size, shape, and material. The reason that's important, by the way, similar size, shape, and material, reason that it's important is because when you have two things that have similar size, similar shape, similar material, and you touch them together, then by the law of conservation of charge, they want to balance the charges out. 0 and -5 become -2.5 and -2.5. -3 and -5 both become -4 and -4. Now, if they're not similar size, if one object is way bigger than the other, then it could hold more charge than the smaller object, right? We used the analogy yesterday of the balcony when we were doing the Van de Graaff generator and why potential difference or voltage doesn't always matter in terms of being dangerous, not always. If you have a really, really big balcony versus a really, really small balcony, the really big balcony can hold more people than the small balcony, right? So we're not going to balance out then. But if we have equal size balconies, then odds are we're going to pretty much balance out. Okay? Now, different shapes, same deal. If you have pointy objects, we can hold less charge than if we have uniform, smooth objects. If we have certain materials like metals, can hold more charge than other, or certain materials can hold more charge than other materials. So we want to have, if we're doing a question like this, we want to know that it's similar size, similar shape, similar material, so that when we go to touch two charges together, like this one and this one, they're going to balance out. We want to find here, when we touch these two things together, what the final charge is on both objects, which object gained electrons and which object lost electrons. How do you think we're going to determine what the final charge is? When I gave you 0 and +5, it was easy, 2.5 and 2.5. When I gave you -3 and -5, it was easy. It was -4 and -4. What do you think these are going to balance out to be? How do you figure that out? It's not hard. What did we do when we did 0 and 5 became 2.5 and 2.5? What did we do when we said -3 and -5 became -4 and -4? What did we really do there? Yeah, right? We average them, yeah. Just add these up, divide by 2. Now, if you happen to have 3 charges that you're touching together at the same time, then we would add them up and divide by 3, right? So let's say 2 times 10 to the -6, which, by the way, is 2 microcoulombs, plus -3 times 10 to the -6, divided by 2. That gives me -1 times 10 to the -6, divide it by 2, which I think when you do that, it gives you 5.0, negative 5.0 times 10 to the negative 7 coulombs. Now, which one is negative 5.0 times 10 to the negative 7 coulombs? Both of them are. Yeah, both of them are. The total charge here, the total charge when I add up 2 and negative 3 is negative 1. No, that's not right. Yeah, that's right. When we add up 2 and negative 3, we get a total charge of negative 1 times 10 to the negative 6. Well, if we were to add this up twice, because there's 2 of them now with 5.0 times negative 7, then we get negative 1 times 10 to the negative 6. By the law of conservation of charge, okay, the total charge has to remain the same, and it has. If we were asked to explain what physics principle we used to identify, to figure out what the charge was on each of these, we would say it would be principle number 7, conservation of charge. Now, which object has gained electrons, which object has lost electrons? Take a look at the one that was positive 2 times 10 to the negative 6, and the one that's negative 3 times 10 to the negative 6. The one that was positive and became negative, because they both became negative, right? The one that was positive and became negative, did it gain or lose electrons? Yeah, if you're negative and you become positive, you must gain negatives, or you must gain electrons. The one that was negative, 3 times 10 to the minus 6, became negative 5 times 10 to the minus 7. It became less negative, right? The exponent is smaller. So it was negative, it became less negative. So therefore, it must have given away or lost electrons. So if you become more negative, you gain electrons. If you become less negative, you lose electrons. Next question has some similarities to the last question, but there's more to it. It says ball number 1 has a charge of 3 coulombs, which, by the way, that's a lot of charge. 3 coulombs is a lot of charge. Right? We said that it takes 10 to the 19 electrons to make up a coulomb of charge. That's a lot of charge. Ball number 1 touches ball number 2, which has a charge of negative 1 coulomb. That's also a lot of charge. And then they're separated. And then ball 1 touches ball 3, which has a charge of negative 5 coulombs. We want to find the final charge on each of them, assuming all of them are equal size, equal shape, and equal material. In other words, that when we touch them, they balance out. Can we just add these up and divide by 3? Dylan, why not? You're shaking your head no. Why not? Good. They don't touch at the same time. These are different events, right? Ball 1 touches 2. That's one event. They balance out, but that's one event. Done. Then ball 1 touches ball 3. That's another event. It's completely separate of that. Okay, let's deal with both of those events separately. The best way to do that, I think, in one of these questions is to create a table. Ball 1, ball 2, and ball 3. Ball 1 starts with a charge of 3 coulombs. 2 is a charge of negative 1 coulomb, and 3 is a charge of negative 5 coulombs. Let's find the total as well. The total charge there, 3 plus negative 1 plus negative 5 gives me negative 3 coulombs. Now, the question says ball 1 touches ball 2. 1 and 2 touch each other. They're going to, because it's similar size, similar shape, similar material, they're going to balance out, right? 3 and negative 1 are going to balance out to be what? This is a multiple choice question. You know what one of the options will be? 2. Is that right? No? Ryan, what do they balance out to be? 1 and 1, right? The total charge between the two of them is 2, but they balance out to be 1 and 1. And number 3 hasn't changed, right? It's still minus 5. Now let's add those up just to make sure that we keep the same total charge here. Plus 1, negative 5 gives me negative 3. So sure enough, I have the same total charge. That means that odds are I'm correct so far. Okay, everything is good so far. Now it says 1 touches 3. 1 touches 3. If 1 and negative 5 touch each other, they're going to balance out to be what? 1 plus negative 5 is neg 4. Neg 4 divided by 2 is neg 2. Negative 2, negative 2. And what about charge number 2? Well, it's still plus 1, right? Because it hasn't it was involved in this event. Add these up. Negative 2 plus 1 plus negative 2 gives me negative 3. So looks like the charge on number 1 is minus 2, number 2 is plus 1, and number 3 is minus 2. Since the total charges remain constant, it looks like I've done this correct. Question said, what physics principle did you use to solve this problem? You would have said principle 7, conservation of charge.